there and talk with you about Lewis structures and how to draw Lewis structures. Lewis structures are a really handy way to represent molecules, and we'll use this a lot in chemistry. And we want to learn today how to write them correctly so we can predict and be able to find the most likely or the most correct of Lewis structures. Okay, Lewis structures are a way to represent atoms. We're going to use this to represent atoms usually in a molecule, but we can reuse this also to represent single atoms or atoms that are in ionic compounds. So if we have just an atom by itself, we'll have just the valence electrons. Notice for something like lithium, which has a single valence electron, that this Lewis symbol is going to be Li with a single dot representing that valence electron. And based upon the Aufbau principle, we'll have the electrons that will spread out first before they start pairing up. So representing the s and p orbitals, so 1s and 3p orbitals will give us 8 electrons. And you may recall 8 electrons is a stable form in the valence shell. So all of our noble gases have 8 electrons in the valence shells. Same principle, we use this to represent atoms. So we can represent single atoms, and things like fluorine will have 7 valence electrons, and you notice that one of those is unpaired, indicated by the single dot. And in this case, our neon and argon are noble gases representing with 8 valence electrons, all of them paired up. Again, these are the s and p orbitals that are being filled up. Okay, so this is a representation to look at molecules and how their three-dimensional structure is represented. So let's look at a few examples. First example is PCl3, and we're going to go through a strategy. I'm going to define for you a strategy to be able to estimate what the structure is likely to be. And we're going to have a couple of ways to look at these. The warning here is that this does require some thought, so you want to be able to look at a structure and estimate whether it's correct. And I'll give you a guide for how to do that, but it does require you still to look at the end to decide if it makes sense or not. Okay, and first of the steps. So first thing we want to do is we want to add up the total number of valence electrons. So phosphorus is going to have 5. Chlorine is going to have 7. I have 3 chlorine molecules, so I add that all together and end up with 26 electrons that will be in the valence shells of my phosphorus and 3 chlorine atoms. If it's an anion, I want to add on that number of electrons represented by the charge. If it's a cation, then I want to remove electrons from that total to represent the deficit of electrons compared to protons. Okay, second step, and then I want to estimate a structure. I'm going to find the least electronegative atom, and I'm going to put that in the middle. Electronegativity, you may recall that the fluorine atom is going to be my most electronegative atom, so that's going to be in the upper right-hand corner. Chlorine is pretty close to that, so one level down from fluorine. Phosphorus is a little bit further away, so chlorine is going to be more electronegative. Phosphorus is going to be less electronegative, so I'm going to stick phosphorus into the middle. And this makes sense chemically because what's happening is we have chlorine molecules that are going to be drawing electrons to themselves. If they're better at drawing electrons to themselves, they won't be sharing as many. Whereas something like phosphorus, to make the structure work, it needs to share electrons, and phosphorus is going to be more willing to share more of its electrons because it's less electronegative. So that thing's just hanging out to electrons less tightly is going to be stuck in the middle, in this case phosphorus. So we're going to draw them there. I'm not putting any electrons there. I'm just going to draw lines to represent the bonds or the sharing of those 2 electrons. So each line represents a bond, and that represents 2 electrons, a pair of electrons which are shared between 2 atoms. Okay, so far I've used up 6 electrons. I've drawn 3 bonds, 2 electrons in each bond, so I have 6 electrons in my structure so far. So I'm left with 20 electrons. Let's keep track as we go along. Okay, now I'm going to go to the outermost elements, and I'm going to fill them up with 8 electrons. Now remember, my chlorine is already sharing 2 electrons, so each chlorine atom I'm going to add 6 more electrons onto that, and I'll add that in the form of dots as shown here. If it was hydrogen, of course, I wouldn't add any more. Hydrogen can only fill up its s orbital, it can hold 2 electrons, so hydrogen will form a bond, and then it's done. It is very stable at that point. It's not going to have any more electrons. Okay, in this case, I've put in my 6 additional electrons around each of my 3 chlorines, so that's a total of 18 electrons that I've added into my structure so far, leaving me with 2 electrons left. Okay, in the next step, I want to fill the octet of my central atom. So finally, I'm going to go to my central atom, and if I have any electrons left, I'm going to put them right on top there. Now I'm done. I have filled up used up all of my electrons, and I have filled up the octet, in this case, for all of the atoms, though that's not necessarily the case. Okay, if in fact I had run out of electrons before the central atom had an octet, then all I can do is shuffle electrons around. Remember, I can't add any more electrons in, but I can move the ones that I have in my diagram in different places. And the best thing to do in that case is to move those electrons from nitrogen into form a double, or in this case triple bond, to allow each atom to have an octet. Okay, the summary. So we count up this whole number of valence electrons. We put the least electronegative atom in the center, except for hydrogen. Never have hydrogen in the center. Fill up the terminal atoms until you either run out of electrons, add up the electrons, see how many are left, add them onto the central atom, and lastly, if needed, you make multiple bonds. At the end, thought is still required. Okay, let's try a few. So I'll do a couple of these, and I'll let you try these on your own if you like. BF3. BF3, so I have boron. This is going to have 3 valence electrons. I have fluorine. This is 7 valence electrons times 3. I'm at 21. Altogether, I have 24 valence electrons I want to have in my structure. Now I'm going to estimate the structure. Fluorine is the most electronegative element, so I know that's not going to be in the middle. Everything is going to be less electronegative than that, including boron. So I'm going to put boron in the middle and just attach my 3 fluorine molecules to this. Okay, so far I have 3 bonds, each representing 2 electrons. I have 6 electrons in my structure out of 24. Now I'm going to add electrons to the terminal atoms. So I'm going to put 6 more electrons around each of my fluorines. I'm going to add this all up, and I now have my 6 electrons that are in bonds, plus an additional 18 electrons that are free electrons around the fluorine atoms, and I have 24 electrons. And that's all the electrons I have, so guess what? I stop there. Boron, in this circumstance, does not fulfill the octet rule. So boron doesn't have 8 electrons around it, but that's fine. I have a valid and correct Lewis structure. I have fluorine, my most electronegative element, has drawn those electrons to itself. It's going to have a very stable and filled octet, so it's satisfied. Boron, not nearly as electronegative. It's not going to hang on to those electrons. It's not going to be drawing those electrons to itself. And in fact, it ends up having less than a full octet, a valid Lewis structure. Okay, let's look at another structure. So it's a xenon tetrafluoride. So xenon, even though it's a noble gas, you may say that it doesn't interact very much, generally very stable. And the small noble gases, so like neon, are going to be very independent. They're not going to interact with other molecules or other atoms. Xenon, though, as you get bigger, xenon and the other noble gases will form compounds. In this case, I can form xenon tetrafluoride, a compound where there will be sharing of electrons. There will be bonds between xenon and fluorine. And that structure will form something. It's going to be a little bit odd, as you can estimate, because xenon is going to have already 8 electrons in its valence shell. Well, let's go through the strategy to figure out the Lewis structure, see if we can come up with the right answer. So we have xenon is going to have 8 electrons, fluorine is going to have 7 electrons. I have 4 of those, so 28 altogether. I'm going to have 36 valence electrons, so my Lewis structure needs to have 36 valence electrons represented in it. First thing I'm doing, I'm going to estimate what is likely to be the structure of xenon tetrafluoride. I'm going to take the least electronegative and put that in the middle. So I'll estimate the structure. It'll look something like this. Xenon tetrafluoride, xenon with just the 4 fluorines around it. And I've put 4 bonds in there, each bond having 2 electrons. So 8 electrons are in my structure so far out of my 36. Next step, I'm going to add electrons into the terminal atoms. So I'm going to put 6 more electrons around all of my fluorine atoms. And in this case, I end up adding 24 more electrons. So I have 4 electrons left after this point. Notice right now I might stop. So I have a very nice Lewis structure. I have 8 electrons around every atom there. So the octet rule for everything is being fulfilled. However, I have more valence electrons, and so what's the next step? I'm going to place those valence electrons around my central atom. In this case, xenon is going to gain 4 more electrons, and now I have my final and complete and accurate Lewis structure, where I have my fluorine atoms, each with 8 electrons around them, fulfilling the octet rule. I have xenon, the least electronegative, sitting in the middle. sharing electrons with fluorine. However, notice it has more than 8 electrons in its outermost shell, and this can happen, and this happened in case of xenon tetrafluoride. Obviously, some electrons from lower energy levels are participating in some of the bonding, and this allows xenon to have a Lewis structure that looks like this. So you don't have to have a complete octet in a Lewis structure, but you will get to the right structure by following the strategy that's been laid out. Okay, I'll leave the other ones for you to try. A couple of interesting ones there that give you some solvable but interesting Lewis structures. Okay, so it is also possible to end up having multiple valid Lewis structures. So let's take the simple case of carbon dioxide. Carbon's going to have 4 electrons. Oxygen's going to have 6. If 2 of those 12 electrons, altogether 16 valence electrons that are going to be in the structure. So we're going to estimate how this should look, how I should put this together. I'm going to put carbon in the middle. I'm going to put the oxygens on the sides. Carbon's less electronegative. And after I do my Lewis structures, I can end up with one of 2 structures. I can have carbon that's double bonded to oxygen on either side. Notice all of my atoms have 8 electrons around them. So I have my atoms represented. I have all my valence electrons represented, and everything satisfying the octet rule. And notice the structure on the bottom. That I have also satisfied the octet rule for every atom, and I have every atom represented. According to the Lewis structures, there is no preference for either one of these. So we have a strategy for figuring out which one is most likely to exist. And the idea is pretty straightforward. So we're trying to figure out where are those electrons likely to be hanging out. Well, what's drawing those electrons is going to be the protons. So we're going to try to find the structure that distributes the electrons across the protons as best as possible. And we're going to have a name for this. We'll call this formal charge. And so the idea is that we want to figure out, well, how are those electrons distributed? Well, we're just going to add up and say, well, what are the electrons around an atom compared to how many were there originally? So we're going to add up what are the valence electrons that we have originally. So we'll look at first case of oxygen. We start with 6 valence electrons. And then how many electrons have been assigned to it in this structure? In this case, in the oxygen on the left, we have 4 free electrons sitting around it. And we have 4 electrons that are in bonds. So we'll just give them half of the bond electrons. So I say, well, this oxygen is going to have 2 electrons that are coming from those 2 double bonds. So altogether, I'm going to have 6 electrons that are likely to be hanging out around this oxygen, and usually it has 6 valence electrons. The difference is going to be my formal charge. So the formal charge on oxygen in this case is going to be 0. Formal charge on carbon is going to be 0. My formal charge on oxygen on the other side is going to be 0. When we look at the alternative structure, the one that has the triple bond, we'll see the first oxygen have a formal charge of -1. My oxygen on the other side is going to have a formal charge of +1. And now I want to decide which structure is most likely. Well, the most likely structure will be the one that has the least formal charge. It minimizes the formal charge. Right? So I take the absolute value and I add this together. My total formal charge is going to be 2 on the structure on the right. It's going to be 0 on the structure on the left. So I'll end up selecting the structure on the left because the formal charge is lower. Okay, let's try an example of this. So we're going to look at this ion, which contains nitrogen, carbon, and oxygen. So it's going to have 5 valence electrons from nitrogen, 4 from carbon, 6 from oxygen. Notice it has a charge of -1, so we'll add 1 electron in to represent that charge, a total of 16 electrons. From this, I can draw 3 different Lewis structures. Notice I've stuck carbon in the middle because it's electronegative, so I'm still following the rules or the guidelines for putting together the Lewis structures. But in this case, I end up having multiple different options just from moving around multiple bonds, double or triple bonds. Okay, so I want to find the one that has the fewest formal charges. Or, if necessary, puts the negative charge on the most electronegative atom. In this case, oxygen is more electronegative than nitrogen. The last structure would be the best choice. So it puts the formal charge of -1, so the extra electron is hanging out on the oxygen, which has the higher electronegativity, is more likely to draw that electron to itself. Okay, and at times more than one Lewis structure exists that's perfectly valid, and the formal charge will be equivalent. And so we'll be left with two structures that can exist. Usually this only differs by the placement of a double bond. And one example of this is ozone, O3. If I draw a Lewis structure for ozone, I can write a Lewis structure that looks like this. So a perfectly valid Lewis structure, I end up having one oxygen double bonded to the central oxygen and one oxygen with a single bond to the central oxygen. So this Lewis structure is perfectly valid, and this Lewis structure is also valid. So I can have a double bond on either side of the central oxygen. I get the same formal charge. There's no difference in electronegativity of oxygens. So I have no clue where to put this. And the best thing that we can do is to say, well, both of these do exist and can exist in some way. And so we're going to call this resonance, and we're going to write both of these structures. So they kind of both exist at the same time. So we're going to draw brackets around it, and we're going to draw both structures and call this resonance. Resonance is a really important thing. So it represents one of the limitations that we have with the Lewis structure. So Lewis structures, we draw a dotted line to represent the sharing of electrons. In this case, the electrons actually are spending an equal amount of time in the double bond on the left and the double bond on the right. Well, those electrons are being shared across all three molecules. And this really can't be represented in a Lewis structure. We don't really have like a line and a half that we can draw. And this happens in important molecules. So the most important molecule that this, or most common molecule this happens in, is going to be benzene. So we have this carbon ring, 6-carbon ring, that has double bonds alternatively between carbons. And this can be in resonance. For instance, we can have carbons that you can write a second Lewis structure is perfectly valid, where the double bonds in different places, and you get the same formal charge, and there's no indication from Lewis structures which one is more likely. And in fact, each of these is equally likely, or another way to phrase this, is that if you look where those electrons are hanging out, you find that half the time, that double bond is going to be between one carbon, half the time it's going to be between the adjacent carbon. So those electrons really are shared equally across this. And it's sort of an interesting thing that happens. We'll get into a little more detail about this when we look at the geometric shapes that these things take. The benzene is an important molecule. Oftentimes we'll represent this in a slightly different way. We'll drop the hydrogens, indicating the double bonds, or more commonly we'll draw a circle in the middle to represent what's really happening. Those electrons are being shared equally amongst many things. Okay, and let me remind you about the things to remember. So Lewis structure is a really handy way to describe chemical molecules and get some idea what that actually looks like. So it's a hint at what the shape might be. Still requires thought. So we have to use electronegativity to place an atom where it's most likely to be in the molecule, and to make estimates about where the formal charge, if there is one, is most likely to be. And again, formal charge is a way that we can estimate which structure is more likely given two alternative but valid Lewis structures. Big thing to remember is a Lewis structure representation. What we're trying to do, we're trying to represent what is really a very small three-dimensional structure, and we're trying to represent it with some stick figures on a two-dimensional page. Obviously it has limitations. One of the biggest limitations is the delocalization of electrons that can happen. So we have a method of describing this as resonance, but it's more than that. It is not just two structures that exist at the same time. It is a different type of sharing of electrons, and we'll get into that in a little more. It's a Lewis structure. It's very useful, but with limitations. Thank you.